Hello everyone. You have already known about recursion from previous sessions and also basics related to counting. Now today we will start the topic related to advanced techniques in counting, and we will finish it hopefully next week. All right, the first technique that I want to talk about is related to recurrence relation. But what is the recurrence relation? Whether a sequence is not or is a part of a recursive definition, this is called recurrence relation. That is any relation that you can imagine which is recursively defined, we can call them recurrence relation. Because you already know about recursion and you know you can define terms based on the previous ones. So that's what we call simply recurrence relation. And when we talk about solution of a recurrence relation, it means that we are looking for a sequence. So this sequence can be the solution of that recurrence relation, but how it happens? So let's go through the examples to see what we mean by recurrence relation and how we can find a solution for it. One famous one is related to Fibonacci. And let's see what is this problem about. So a young pair of rabbits, one female, one male, is placed on an island. A pair of rabbits does not breed until they are 2 months old. So until they are 2 months old, it's not possible for them to have children. After they are 2 months old, each pair of rabbits produces another pair of each mount, as shown in figure 1. It means that exactly when the second mount is finished, then they will have 2 children, a pair of children or 2 children. And again, those children, after 2 months, they can start their own family and again have a pair of children. But it's limited, you know. It's like they are forced to have baby exactly at the 3rd month, and each time they have exactly 2 children. The only child is not allowed, apparently. Okay, so in this example, let's see whether we can find a solution for such a recurrence relation. Why we call it recurrence relation? Because it can depend on the previous states. Like before, for example, we had an equal to an minus 1 plus something, for example. Then you see it depends on the previous terms. So we have such a case here too. So in the first month, so you see month by month, we are going forward to see about the terms that we can come up related to this recursive relation. So in the first month, we have a pair of rabbits. Let's call it pair 1. Then in the second month, we have the same situation because, as we mentioned, they cannot have children until the 3rd month. So still they are the same rabbits. And in the 3rd month, they will have babies. So here you can see in this column, we consider these rabbits are at least 2 months old. Here they are the young ones, they are the children. So these ones are not children anymore, they are parents. So actually we consider them here. Okay, so these rabbits that we talked about, they are now here. And they can now have children. So one pair of children, and we call it number 2, pair number 2. In the 4th month, so the same parents are already here. And the same parents, again, they can have baby in the next month. This is the condition. If you read the conditions carefully here in this example, then you see this is the condition that each month they can have baby, but before the 3rd month, it's not possible. For 2 months, it's not possible for them. So here, this is exactly the same children, which is related to pair number 2. Now they can have again another pair. in the next month. And this procedure continues. Let me again continue at least to the 5th month, and you get the idea. Okay, now you see the pair number 2, it has been 2 months for them. So they are already grown up. So this is pair number 2, because in the 3rd month they are already grown up, so they are now inside this column instead of the 2nd one. And this is the same parent that we had at the beginning. So the 2nd one moved here. This is the 3rd one. Now we have 2 parents now, 2 pairs, and each one of them, they can have 2 children. So again, we can call this one 4, this one 5. And you see the number of pairs here is constructing a sequence. And whether this is a recursion case or not, we can check it. You already know how to do that. In the midterm exam, also, we ask questions about recursion, and you already know when you have a sequence how to find out about the recursive definition of that sequence. And this type of sequence, we call them Fibonacci. And whenever you hear about it, because it's pretty famous in mathematics, we use them a lot. So it's a type of recursive relation, as you can see. And you can find about the solution of this recursive relation by considering this sequence. And consider the first 2 terms as 1, 1. It is possible sometimes to define a sequence like this. Like in the midterm exam also, you had a case that for your terms, because of this term we had inside the sequence, it could changes odd numbers of your terms and even numbers of your terms, and they could give you different numbers because of that. And you could also consider, for example, A0 as something, A1 as another number, and based on them define your terms and consider n minus 2. It was one way. It was also another way to consider the previous term, and some of you already I checked and you have already done it correctly, which was good. But anyway, the thing is that sometimes you can start your first terms by some fixed numbers like this, and starting from another number, like say, for example, if n is greater than or equal to 3, then we should have such a recursion type of the sequence. Okay, so here I can define each term as the previous one and 2 states before that. And this sequence, we call them Fibonacci. If you consider each one 1, and I mean F1 and F2 as 1, and starting from the 3rd, then you will have such a recursive type of definition for your sequence. So now you saw for a recursive relation, you found a sequence as a solution for that. And it's not always as easy like just to write the terms and understand about it. Sometimes it can be trickier than that. We already practiced with how we can give some terms and find it, and sometimes it gets much complicated. So we need to know about some theorems, maybe we should prove them and then use them in our problems in order to solve them easier. Okay, one of the linear recurrence relation that we can talk about is related to this one. This one is linear homogeneous recurrence relation. And you see, for each one of the terms, which are starting from A0 or A1 here, we should be also careful about that. Let's see how they define it. They define the multiplications as 1, 2, 3 until k. So here again for n, I should have started from, it can be started from 0 actually, because if you consider a constant For example, assume that here I have a C0. It is possible also to consider like this. Anyway, now you can see for each term I can consider the recursive relation and define it by its previous terms. So one term before it, two times before it, and so on. And each one of them, they have multiplication. And there is a condition for that. It says that it's not possible for one of these multiplications to be 0. So that's how we define exactly this type of recurrence relation. If it doesn't have these conditions, then we have a different kind of recursive type of relation. Now let's go to through this theorem, which is very important. We want to solve examples related to it. Also for the exam, we are going to ask similar questions related to it. We will, of course, practice it in our weekly assignment as well. So let's go through this one carefully. Let C1 and C2 be real numbers. So they are real numbers, C1 and C2. Suppose that R power 2 minus C1 R minus C2 is equal to 0. We already defined C1 and C2 as real numbers. So what is R exactly? And we will talk about it also here about R2, but this R is different from R1 and R2. These one are just variables. So these R's that you can see, you can even show them by X instead of R. R power 2 minus C1, R minus C2. Instead of C1 and C2, you can consider real numbers. And these two are variables. So if you solve this equation, you will find two distinct roots for that. And it's not always the case for quadratic equations. Do you remember that you had delta method? If you don't remember about delta method, please go back through your lectures related to pre-calculus and remind yourself about delta method. That in case that we had delta as a positive value, then we knew that it has two distinct roots. Now we want to only talk about the cases when delta is more than 0. If this is not the case, then we cannot use this theorem. Okay, so if we have such a quadratic equation and it has two distinct roots R1 and R2, then we have this relation. What is that? The sequence AN is a solution of the recurrence relation, this equation. So C1 and C2 are exactly as these numbers that we used here, two real numbers, okay? And AN minus 1 and AN minus 2 are defined recursively based on AN, okay? So this condition holds if and only if AN is equal to this for all non-negative integers. And alpha 1 and alpha 2 here are constant. So what does it mean? When we say if and only if, it means that this sequence is the solution of the recurrence relation. If this is true, then this term is also true. We have such an equation. Vice versa, we could say the same. Like if this equation is true, then we could say we can find the sequence as a solution of recurrence relation. So let's see in examples which are much easier, most probably as the definition as you saw, but they are pretty easy. As soon as you see examples about them, you will see that the theorem is very easy to use. But we should be careful anyway not to insert or assign values which are not related to that theorem. All right. Now, what's the solution of the recurrence relation, this one? If we know two terms of that, we know, for example, A0 is equal to 2, A1 is equal to 7, and you can continue to come up with the rest of the terms. But now we are looking for a solution of the recurrence relation, which is new for us. We didn't do it before. Now, how we can do it? This theorem is called Theorem 1 in this chapter. So whenever we refer to theorem number 1 in this chapter, it's related to the one that I mentioned in the previous slide. Okay? So Theorem 1 can be used to solve this problem. The characteristic equation of the recurrence relation is this one. How did this one came up with this? How did we understand about it? By looking at the multiplication of an minus 1 and an minus 2. So what's the multiplication of this one? This is, let's say, 1. And what is the multiplication of an minus 2? This is 2. So if I go back here, you see C1 now is 1. So if I say R2 minus C1 R minus C2, now just assign the values in them one by one. So C1 is 1 and C2 is 2. That's why here we have this equation. Okay. So by using any method you like, you can find the roots of them. And I suggest you guys to remind yourself about delta method, which is very basic and I think everyone should know about it. But if you don't in any chance, then please remind yourself about delta method. So in that scenario, we understand that the roots of R, which we can also call them R1 and R2. So you can also call them R1 and R2 so that it reflects exactly the same type we used inside our equation here. You see, here we used R1 and R2. We named them that. So there are two distinct roots. Now, the sequence AN is a solution to the recurrence relation if and only if we have now such a case. So based on the theorem that you come up with this equation and you found the roots, then you can define this equation. So if you go back again to this theorem, you see that we should have two constant, alpha 1 and alpha 2, but I don't know the value of them so far. And we have power n for R1 and R2 separately. So we already calculated R1 and R2 based on the previous equation. So now that I have R1 and R2, I just simply assign it into this equation instead of these two numbers. So one of them is 2, so I will have 2 power n. The other one is minus 1, so I will have minus 1 power n. So now I should find out about what's the values of alpha 1 and alpha 2. There are two constants. How can I find out about them? By using these two terms, because I know about them. A0 in this sequence is equal to 2. A1 is equal to 7. So I can have two equations, two unknown variables, and easily solve this problem for alpha 1 and alpha 2. So I already know that alpha 0 is equal to, A0 is equal to 2. And if you insert it inside that, you see this equation now that you have, instead of n, whenever you see n, consider 0. So 2 power n, it is 1, and minus 1 over power n, it is 1. So what you have, alpha 1 plus alpha 2. So that's how we come up with this part. So I already know from the assumption that A1 is equal to 7. It means that consider n equal to 1 inside the previous equation that you finally found here, okay? And if you consider here 1, you will have 2 alpha 1. Yes, 2 times alpha 1. And here I will have minus 1 power 1, which will be 1 multiply, minus 1 multiply alpha 2. In the book, they usually consider points as multiplication, I usually don't prefer that because sometimes we make mistake. We cannot distinguish between this one and decimal points. I usually prefer to consider parentheses in order to show multiplication, something like this. So if this one is simple, actually you could just easily write it without any space between them. But if you have extra terms, something like that, then again you could use parentheses and easily show that. But whenever in the book you see this point, it means that we are talking about multiplication. Anyway, now you have two equations and two unknown variables, alpha 1, alpha 2. Again, from high school or pre-calculus, you know how to deal with them. If you don't, please again go through your lectures and remind yourself how to find out about them. Because sometimes we will have maybe 3 equations and 3 unknown variables, and then you should practice with it at least a few times so that you remind yourself how to do that. Because as you know, in the exam, sometimes the time can be limited for you if you don't know how to deal with calculations. And if you have lots of calculations in the exam, then it could be tricky for you. So it's nice that you go through all the examples and try to solve them yourself before looking at the solutions, because the solution is very easy as soon as you look at them. But if you want to solve it yourself, sometimes it can be time consuming or tricky sometimes. Okay, now assume that after solving these two equations, I mean 2 is equal to alpha 1 plus alpha 2, 7 is equal to alpha 1 multiply 2 plus alpha 2 multiply minus 1. Now, based on this, you can easily find alpha 1 and alpha 2. And as soon as you find it, let's see what happens. Hence, the solution to the recurrence relation and initial condition is the sequence. So this is the solution. The solution is always a sequence for such recursive relation, okay? We should be careful always. Whenever we talk about the solution for a recurrence relation, we are talking about the sequence. Okay, this is such a sequence such that for each term we can define such a thing, okay? So if someone just write this as the final answer, this is not correct. You should say this is a sequence an, and you show it inside these curly brackets, okay? Usually show a sequence inside curly brackets like this. So there is a sequence named an, and for each term of that I can have this. So you see 3 and minus 1 we found out for alpha 1 and alpha 2. How did I come up with this equation? Again, let me remind you why we are looking for alpha 1 and alpha 2. Because see, in the previous slide, we reached this one actually. We reached this one, we didn't know what is alpha 1 and alpha 2. As soon as you find them, then you can just replace alpha 1 and alpha 2, and you will find the final answer like this. A sequence that for each term you can find like this. For an, for example, if it is a3, just consider n as 3 and you find the new term, and so on. So there are so many theorems related to linear recurrence relations and even different types of recurrence relation. This one actually was the easiest one. So we tried to see at least some basic one. As soon as you see this one, as soon as you understand it, I'm sure you can easily understand about other ones, but I consider it as extra reading. So you should know for the linear recurrence relation related to the first theorem, that's it. And for the weekly assignment, we will also practice it together, because this one for sure needs practice so that we get used to it. Don't underestimate it, because it looks easy at the first sight, but we should practice with it so that we won't have problem and we won't have any miscalculation, because miscalculation can happen often if you don't practice with this one. Okay guys, that was for this lecture. For the next week, we will deal with other advanced techniques in counting. I will talk about a specific algorithm which is related to your major, computer science or computer engineering. and also we will talk about generating functions, which can be very useful. Okay, guys, if you have any questions, please let me know. And if you have any comments about the feedback related to your midterm, you should wait until 21st of December. And from that time, you can ask me those questions using email.